A turboprop engine is a type of turbine engine that uses a turbine to drive a propeller, which generates most of the engine's thrust. In this detailed description, we shall examine the working principles, design, and engineering of turboprop engines. A turboprop engine operates on the principle of extracting energy from a gas turbine and using it to drive a propeller. The process can be divided into three main stages. 1. Air intake and compression. The engine draws in air through an inlet, which is then compressed by a compressor. The compressor is typically a multi-stage axial compressor, which increases the air pressure and temperature. 2. Combustion and expansion. The compressed air is then mixed with fuel and ignited in a combustion chamber, also known as a combustor. The combustion process releases a large amount of energy, which expands the gas and increases its pressure and temperature. The hot gas is then expanded through a turbine, which extracts energy from the gas. 3. Turbine and propeller drive. The turbine extracts energy from the gas, which is then used to drive the propeller through a reduction gearbox. The propeller converts the rotational energy of the turbine into thrust. A turboprop engine typically consists of the following components. 1. An inlet. The inlet is responsible for directing air into the engine. It is designed to optimize airflow and reduce drag. 2. A compressor. The compressor is a critical component that compresses the air. It is typically a multi-stage axial compressor, which consists of multiple rows of blades that compress the air in stages. 3. A combustion chamber. The combustion chamber is where the fuel is ignited and the combustion process takes place. It's designed to withstand the high temperatures and pressures generated during combustion. 4. A turbine. The turbine extracts energy from the hot gas produced during combustion. It is typically a multi-stage axial turbine, which consists of multiple rows of blades that extract energy from the gas. 5. A reduction gearbox. The reduction gearbox is responsible for reducing the speed of the turbine output to a speed suitable for the propeller. 6. A propeller. The propeller converts the rotational energy of the turbine into thrust. It is typically a variable pitch propeller which can adjust its pitch to optimize performance. 7. An accessory gearbox. The accessory gearbox drives the engine ES accessories, such as the fuel pump, oil pump, and generator. When designing a turboprop engine, several factors must be considered. 1. Power-to-weight ratio. The power-to-weight ratio is critical in determining the engine's efficiency and performance. A higher power-to-weight ratio generally results in better performance and fuel efficiency. 2. Thrust-to-weight ratio. The thrust-to-weight ratio is also important as it determines the engine's ability to generate thrust relative to its weight. 3. Fuel efficiency. Fuel efficiency is critical in determining the engine's operating costs and environmental impact. Turboprop engines are generally more fuel efficient than other types of engines, especially at lower altitudes. 4. Reliability and maintainability. The engine's reliability and maintainability are critical in determining its overall performance and operating costs. 5. Noise and vibration. The engine's noise and vibration levels must be minimized to ensure a comfortable and safe operating environment. The engineering challenges in the production of a turboprop engine. Designing and engineering a turboprop engine poses several challenges. These challenges can be very daunting, and they include optimizing the engine's aerodynamic performance is critical in achieving high efficiency and thrust. Secondly, managing the engine's thermal performance is essential in maintaining its structural integrity and preventing overheating. Thirdly, the engine's mechanical components must be designed to withstand the high stresses and loads generated during operation. Fourthly, the selection of materials is critical in determining the engine's performance, durability, and maintainability. Furthermore, integrating the engine systems such as the fuel system, oil system, and electrical system is essential in ensuring reliable and efficient operation. The turboprop engine industry is constantly evolving with several advancements and trends. Advances in materials science, aerodynamics, and thermal management are leading to more efficient engine designs. Engine designers are focusing on increasing power density, which enables more powerful engines to be installed in smaller airframes. The industry is moving towards reducing emissions, with a focus on more efficient combustion systems and alternative fuels. The use of digital technologies such as advanced simulations and autonomous systems is becoming increasingly prevalent in engine design and development. Finally, the industry is exploring the use of sustainable aviation fuels, which can reduce greenhouse gas emissions and dependence on fossil fuels. Some notable examples of turboprop engines include 1. The Pratt & Whitney PT6. The PT6 is a popular turboprop engine used in a wide range of applications, including business jets, commuter aircraft, and military aircraft. 2. The General Electric CT7. The CT7 is a high-power turboprop engine used in military and civilian applications, including the C-130J Super Hercules and the Saab 340. 3. Rolls-Royce AE2100. The AE2100 is a high-power turboprop engine used in military and civilian applications, including the C-130J Super Hercules and the Shinmaiwa US-2. 4. Ivchenko Progress D27. The D27 is a high-power turboprop engine used in military and civilian applications, including the Antonov An-70 and the Ilyushin Il-76. Turboprop engines are complex machines that require careful design and engineering to achieve optimal performance, efficiency, and reliability. The industry is constantly evolving, with a focus on more efficient designs, reduced emissions, and increased power density. As technology advances, we can expect to see even more efficient and powerful turboprop engines in the future. New technologies designed for turboprop engine upgrades include the lightweight composite materials for propellers and engine components, reducing weight and increasing durability, and the precise management of engine operation, optimizing fuel consumption and performance through full authority digital engine control, FADEC systems. Other improved systems include the hybrid electric propulsion system, which combines traditional turboprop engines with electric motors for greater efficiency and reduced emissions, and the additive manufacturing used to produce complex engine components via 3D printing, which reduces part count, weight, and improves efficiency, as seen in GE Aerospace's Catalyst engine. Advanced aerodynamics with improved airflow and reduced noise levels, enhancing overall efficiency and passenger experience, and sustainable aviation fuels, which is compatible with biofuels and synthetic fuels, which consequently reduces dependence on fossil fuels. The Rolls-Royce's upgrade for T56 engines offers 7.9 to 13% fuel efficiency improvement, lower operating temperatures, and improved high-altitude performance. These technologies aim to improve fuel efficiency, reduce emissions, and enhance overall performance in turboprop engines.